Hello, folks. Rashid here. Thank you so much for joining. Okay. In previous video, I promised that today I will start on Python implementation of R and I type instruction into machine language. But you know what? Little bit change of strategy for good reasons. Okay. I know I'm also very excited about it. But let's finish the theory. Today we have SB type, and after that we will look into U and J type. Okay, so let's finish the theory so that we all the theoretical knowledge we have, because when we start doing coding, then we might be improving it, enhancing it. That might take a little bit time. It's area. Then I'll get more involved there, and you can get more involved there, right? Okay, so a little bit more weight. So today we will look into SB type. So we look into R type, then I type, and we have SB type, not single but two, not BS type, but SB type. Okay, S stands for store, B for branch. And this time I put those instructions right away as opposed to starting with the field. So yeah, I'm learning. So if you look at, these are the three: S type, SB, SH, S half word, S word. Word is full, right? 32 bits, and this 16-bit, and this applies as 8-bit. Opcode always keep the least significant bits for that, and that is 35 for these. Func 3 we will keep again, and these are three values to differentiate among them. Similarly, B type or branch types are these ones. Okay, so if you look at today is the pink color day, and so these yellow, you remember, those were R type. Green are sorry, these are R type, these are I type, and these pink ones will be what? The SB type. And tomorrow we'll do some more coloring. Make sense? All right, so we will look into first S type. So again, I kept this table there, and also a register mapping is there because we typically write in these, but when we convert, it's much easier, especially our decimal table. First, we use decimal values. So for example, T1, we will put 6. Okay, and then we convert into machine language. I think this is where we will spend more time. So yeah, here is the instruction format. So format is that 0 to 6-bit is opcode, as always. Okay. Now in these instruction, if you look at store word, store half word, store byte, they have two registers involved. Now none of them is a destination register, because you know what happens. Let's look into this one. So what we do typically, in case you forgot, this register here has a base address, and then we add this value to it. Okay, and that generates a 32-bit address, and at that address in the memory we write the content of T2. So both are these source registers. None of them is a destination register. Got that? So this destination register place is not, we can reuse it for what? For immediate. So immediate for the S type instructions is 12-bit. Okay, so how those, so you know that this is 3-bit, right? So this is 7-bit. So then remaining are 5 bits here, and how many? 7 bits here, right? 5 till 11. 5, 6, 7, 8, 9, 10, 11. So including 5 or 11, those are 7. So this is 7. Sorry, this is 7. And this is 5. Together makes 12. So not a big deal. And you have seen that instead of saying that, okay, we keep 0 to 4 here, and then 5 to 9, the immediate will be the same. But if you look at, we are keeping, so when this structure is formed from the hardware implementation, which will later on, This we always RS1, RS2, wherever if they are in the instruction, we don't have to change the wiring. They're always pointing to the same kind of bits of the instruction. So small decision like those can have a bigger impact on the actual hardware, less number of wires. Less change of hardware to decide is this type, then do this wiring, is the other type, then do this wiring, right? So these specs are created to generate identical, replicated, simpler hardware. Make sense? And when we start implementing in system Verilog, that's where you will appreciate this. So we keeping RS1, RS2 same place, and RD place is empty, so we are using 5 bits here and rest of the bits here. So let's look at this example. Store word S3. So 35, right? 2, because it's this. And then RS1 is this, S3. S3 is 19. T2 is 7. Makes sense? So this taken care, this taken care, this taken care, this taken care. Good. So the only bits are here. This is a negative number, -6. So again, if you don't remember how to calculate 2's complement, go back and watch my 2's complement series. Not in this course, but if you go to YouTube channel, there is a logic design series, and inside I've discussed that. So 2's complement is 0, 1, 0, 1, 1. And then the sign bit is extended, as you know. Again, sign bit extension, I think I did talk about maybe earlier in this course, but I also have sign extension in that logic design series. Look under subtraction, addition type of or boundary conversion numbers. Simple, right? I'm not gonna, there's nothing different here. This is a different instruction. This is just an hexadecimal. You look at this 2D. So a D is this, 4 bits, and our 2 is 0, 1, 0. Rest is simple, straightforward. Then the second part, okay, before we go to second part, I wanted to create a little bit a further explanation. I think you got what I wanted to say. So this is again for the S type. So what we do is, we calculate the address. This instruction is eventually has to calculate the address where we have to store the content from RS2. So this is RS1 value. So you can say that, okay, yeah, I should have maybe this one. RS1 goes here. And this is because of this is a register. So this instruction, reads the contents. This value needs to go to RS1. So actually, oh man, I'm missing it. So this says the value of RS1 we need to read. So RS1 is already here. So we need to read the content of this register. RS1, whatever, S3, S2, whatever the instruction has. So that content is already in this register, and this register was 32-bit. We need to add an immediate, and our immediate is 12-bit sign number. But when we are adding the two, this number that we are feeding into has to be 32 bits, and those 32 bits we're adding. Keep this in mind, this is not a register. Okay, I'm just creating a bus of 32 bits. So instead of using this, I'm using this long green solid line. These are individual bits. And these 32 bits are calculated from this instruction. But you're thinking that instruction has only 12 bits. So we're building from 0 till 4. The first 5 bits, we take the wires. From this instruction goes into this. We bring the instruction outside, and then that's where those bits go into there, the data that we're getting from the memory. So with the data we're getting from the memory will go there. Then the next bits from 5 to 11 go here. The 11th bit, which is 11 means 12 bit, right? because we start from 0 till 11. So 12 bit is replicated all over this place because this is the sign bit. If it's 0, find 0. If it's 1, it goes down the way. You understand that? Because this one is really in terms of this operation, this is the sign bit. So even though you have a 12 bit, but actually when we feed it to the adder or ALU, we have to create a 32 bit number. The other is simple, it's already 32 bit. This concept is important because this concept, I hope you already had that even for the I type, but I thought it's better to explain this, and it's going to be more useful in the explanation of the B type. So this is B type instruction, and I kept S type. Like, by the way, all these tables are from the book, and book is really good. I mean, full credit to the authors, Sarah and David, by creating really good examples that I didn't have to create examples. So I give a full credit to them, and you should buy their books. Yeah, they have multiple books on this RISC-V series. Okay, so now look at the B type. B type is again similar to above one. There are a little bit changes. So this is up, and we know that up code is 99, and then these 3 bits are function 3, just like S type. This is RS1, RS2, because see, this is the instruction. This is one of the instruction example. Branch equal to. So don't worry with a lot of stuff here. Follow what I'm explaining, and that will be easier for you. So BEQ, branch if equal. So we're comparing S0 and T5. We're comparing them. Okay. And then if equal, then we're branching to L1. And that example is here. So there's a little trick here involved, and it's important that you understand that this instruction, so here in this example, pretty good example, it says that this instruction is there on memory address this. I mean, we haven't put all the 32 bits of the address, only 8 bits. So this hexadecimal location, we have this instruction. We read, our CPU reads this instruction. So, and then we fill the instruction field. Let's understand this thing, which is over here. So our CPU sees that 99, that means it's a branch, which means, and then it goes into func 3 parts, and then also sees that, okay, that is this branch equivalent, not other ones. Now it knows that this is, I need to compare RS1 and RS2. Okay, and S0 and T5. And if they're equal, you need to branch to L1. What is L1, if you remember? L1 is where this is L1. So if they're equal, you need to jump there. Now the jump, the way it is, we don't put the address 80 here. What we do is we put this L1, we replace it with the address, which is an offset relative to this one. So this instruction is 4 words down in this, or up, whatever. So you go from here to here. Remember, each address has increment of 4, and we talk about that thing in the memory architecture. If you don't remember, go back and watch that video. So each time is 4. So that means this instruction is 4 word, down or up. In this table is down. Okay, and this 4 times down. So we 4 times 4 is 16. Make sense? So this on memory is byte addressable. So we have address 0, 80 for 1, 8, 1 for the second, 2 and 3, and then it's go, sorry, I should have, and then it's go 4, 5, 6, 7, 8. I don't have the memory space, but remember that each byte has a different address. So how many bytes down we need to go? 16 bytes. So L1 is 4 instruction past BEQ. So if you thought that this is actually the absolute address, it's not absolute address. This is an offset relative to this. So this number is 16. So in the immediate, we need to save 16. And what is the equivalent of 16? You know that, right? So if that one is 0, 1, 2, 4, 8, 16. So ideally I should have bit 0 of immediate, and keep that in mind, the address, we only have, if you look at, we only have 12 bits here remaining. 5 here, 7 here, 5 here, 7 here. So we can only store maximum 12 bits here for the offset relative to this one. But actually, as you move by 4, it happens that you always land at an even number. Means you always land where the least significant bit is 0. I mean, the boundary has 0 and 1, right? So 0 is even, 1 is odd. So when I say even, that's you always land on with more least significant bit is 0. Actually, you can say that both the least significant bits are zeros, 0, 0. But there is a compatibility to 16-bit CPU, so just assume that, okay, always the first bit is 0. I know you probably got confused, why is bringing 16-bit? It's a 32-bit processor, but there is also a 16-bit version. And in 16-bit version, you have what? 16-bit, 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 16-bit. And right now we have 32. So right now, at least 2 bits are always kind of 0 here. But in the 16-bit only, first bit is 0. So in order backward, or same compatibility, again goes back to the same hardware simplification. So we just, here we can say that this least significant bit is always 0. So whenever it jumps, it always lands on this one. The least significant bit is 0. So what's the point in storing 0? Is if it's always going to be staying 0, what's the point of storing that in this format? Right? So that's why the least significant bit, so if I put 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So actually, the actual offset is 13-bit, but the instruction is carrying only 12-bit because we have a space for 12-bit. So we only store this, and bit 0, I explained you in a minute, is always stays 0, so we don't need to store it here. So that's why this instruction starts with 1, not with 0. Clear? Now you probably be wondering, Rashid, okay, that's great. You should have started with 0 here and go to 0 to 4 to 5 here, and then you do go 6 to here, right? Or go to 1 to 5, use something like that. I mean, why you have 11th bit here and then you use 12-bit hit here? So there is this bit swizzling is used, and that is what I'm going to explain you. Okay, I'm doing it very slowly. So I just realized this is not a, this is a comparator, okay? Better, a comparator is subtractor, but okay, so this comparator again goes back, needs 32-bit ALU, the other needs to be 32-bit. One of them is coming from, actually in our case, this one, if you look at, okay, I think I did it totally wrong. Okay, so we are comparing these two, and then this is the offset address. Okay, and that we need to add to what? Add to this value, plus 16, so that it goes here. Okay, so it's not a comparator, I'm sorry. So this is something we need to add to the PC. So remember, when we create a hardware, we will add a actually the PC. So this one, in this case, oops, sorry guys, I wasn't expecting this. I thought what I did was right. Actually, you know what? Let me do this. This is still adder, but this one is PC. PC had was storing this program counter. Now program need to counter goes to this one. Well, let's not focus on the beauty. Okay, so this one we need to jump. So we're not giving 80, we are giving 16. So add this plus 16. You understand that? That's the instruction. So here we need to give the number 16. This is not coming from a register. It's the same way in the previous example. This information is coming from the instruction, the data line coming from the memory. So here as we are building this 32-bit, and there are reasons why we are doing this kind of a messy connection. It looks here messy, but later on for hardware it will be simpler. And we will do the hardware. So bit 0, the way we are calculating, always putting 0. So the next bit that immediate that we are getting, okay, so from what we are saving is immediate 1 till 12, which is again, it's 5 bits here and so on. We are not making 13-bit here or only 12 bits. We're just calling it that immediate only 1 to 12 is stored here. So 1 to 4 bits. We are just connecting them here. 1 bit here, second here, thing here. So this one we gave to this one, this 2 we gave. Okay. So far we have covered 5 bits. Then this 6-bit number 0 to 5 here, so I call it 5 here. This 5 goes here, and this 5 to 6 entire bus comes here, this wiring. Right? 5, 6, 7, 8, 9, 10. So these 6 bits come here. The bit 11 of this, we store here. That's the point I was trying to explain. So this we store here, and that goes here. You probably be thinking, what's the point of storing here, one here? This again. So now look at this one. So bit 12, always the sign bit. So, and we want to keep this one. So bit 12 is coming here to the bit here and then replicate it. So that is one we are keeping, so that is identical. And here, rest of the bits are same 1 to 4, just like the S type. So if you look at the first bit to 4 bit same, and this one, we just making room here. In that case, we are just detecting if it's a B type and S type, and based on that, we will just have a simple hardware for the direction of this one. Rest of the bits wiring will be identical. When we actually implement later on, you will see it. So even if you haven't understood fully, think about it a little bit more, you will understand it, in order to make sure that most of the wiring is similar to S type. We are keeping these bits coming here. So if you remember that, these bits coming here together. The only difference is here, the first one, we are only hard wiring is 0. So here, this one comes to the first one. but here we just will convert that. That's a simpler change. Okay, I hope I have explained it well. If not, it's not end of the world. Okay, we will look into these things again. We will try with Python later on. We will look into everything again when we start creating hardware in system Verilog. So it will be clear later on. So yeah, that's it for tonight. Tomorrow we will look into UJ type. And until then, see you.